All right, let's look at the renal corpuscle in a little more depth. So again, the renal corpuscle consists of the glomerulus and the glomerular capsule, and this is where filtration takes place. Now, this is cool. Check this out. Okay, so again, afferent arteriole, glomerulus, efferent arteriole, and here you have the capsule, right? The glomerular or Bowman's capsule. Now notice what this is made out of. So the capsule is made out of this simple squamous epithelium, and it is actually continuous with what we'd say is a visceral epithelium of these capillaries in the glomerulus, right? These, again, purple kind of wrapping the capillaries. And then you have the glomerular space in between them, all right? Now, what this ends up, right? So as you look at the renal corpuscle, right, they're showing you simple squamous epithelium as the capsular epithelium, simple squamous epithelium, or this visceral epithelium surrounding the capillaries. Its role is filtration of the plasma. So here's what happens. This visceral epithelium is made up of cells called podocytes. Right? They're wrapping the capillary, but they have these little feet and they don't wrap it completely. And so what we end up finding is that in filtration, anything that's going to get through here has to be able to fit through between the feet of the podocytes, the pedicels, and those are called filtration slits. Now notice, this filtration membrane, that's a better way to do it, the filtration membrane, i.e. our coffee filter, what things need to get across, is really made up of three things, right? So we know we're in a capillary. We know capillaries are made of endothelium. And what you might notice is in this capillary, they're actually pointing out the pores. Do you remember what kind of capillary had pores? If you said fenestrated capillary, you are correct. So the filtration membrane is made up of the capillaries, these fenestrated capillaries, right? So there are pores in them. We also have this, what they're calling the dense layer. It's essentially the basement membrane, right? Always underlying an epithelium. And these podocytes, right? And so together this makes the filtration membrane, and again, things don't go through the podocyte so much as they go through these slits. And so we're set up here to have this really fine filter, right? Not everything is going to leave the blood. Big things are going to stay behind. Okay. Okay. Before we look at the mechanics of that filtration, a couple other things I did want to point out. Notice here, right, they're showing capillaries, right, our whole filtration membrane here, into that capsular space. That's where the filtrate is going to end up. But notice what they're showing here. There's this cell, this mesangial cell, that is actually smooth muscle, and it can contract and adjust basically blood flow through these capillaries, through the glomerulus. And then the other thing I wanted to point out is what's called the juxtaglomerular apparatus. Right, or complex. This is a cluster of cells that you'll notice is kind of wedged in here at the base of the afferent and efferent arterioles. And this is my favorite part. This is not accidental. This is a tubule that they're showing kind of coming in, wrapping up behind the glomerulus, and this is the distal convoluted tubule. So the juxtaglomerular cells are right here at the base of the glomerulus and also next to a DCT. So they're between the afferent and efferent arterioles and the DCT. Juxtaglomerular cells are where renin is made. Okay, so we will definitely be coming back to that. So I wanted to point it out because that's really happening here right at the glomerulus. Okay, so we have our filtration slits, we have our filtration membrane. Let's look at how, or the forces, I suppose, that affect glomerular filtration. Now, this should remind you a lot of when we looked at kind of blood flow through the capillary bed and we had filtration and reabsorption, right? So we have a lot of different pressures acting here, and what we're looking for is what forces are causing us to produce filtrate and what forces are opposing the formation of filtrate. When we add those all together, we get what's called net filtration pressure. Right, net filtration pressure, right? And that's going to tell us how much filtrate we're actually forming. So the forces that we're looking at here are the glomerular hydrostatic pressure, or GHP, glomerular hydrostatic pressure. And this is essentially blood pressure. Remember we said it would come in all sorts of different names. We had capillary hydrostatic pressure before, right? This is in the glomerulus, that is a specific capillary, the hydrostatic pressure, the blood pressure pushing up against our filtration membrane. And you can see it's a pretty good force in this example. It is leading us to make filtrate. Our opposing forces are blood colloid osmotic pressure, which hopefully you remember. All right, remember this is the colloids, big plasma proteins and cells that are left behind pulling, that attraction of pulling water back out of the filtrate in this case, right? So this would be, how do I want to draw that? The glomerular hydrostatic pressure is forming filtrate. It's basically going from the blood and actually pushing things into the filtrate. This one is kind of pulling things back out of the filtrate and towards the blood, right? So opposing the formation of filtrate. And then our last one here is capsular hydrostatic pressure. They use the CS instead of C, because remember C was capillary hydrostatic pressure, so this is capsular hydrostatic pressure. Okay, this is basically as the filtrate is filling up that capsule, it starts pushing back against the filtration membrane, right? So this is another pressure that is opposing the formation of filtrate, right? Pushing things back into the blood. So overall then, if you add those forces together, you get the net filtration pressure. Here, the way they've set this up, right? Under normal circumstances, it's approximately 10, right? 10 millimeters of mercury, because again, it's a pressure. Now, what we do with that is that net filtration pressure is then going to determine basically how much filtrate we're actually making. So the let's see if we got a glomerular filtration rate then is the amount of filtrate produced each minute. Right, so kind of like cardiac output was the amount of blood pushed per minute. This is the amount of filtrate produced each minute. And what we'll see is that we end up making about 125 milliliters of filtrate per minute, right? And if you do the math, in a day, you would make about 180 liters of filtrate a day. Think about that. Do you pee 180 liters a day? No, you do not. And so that should tell you that we actually reabsorb most of that. We end up reabsorbing something like 99% of what we put in the filtrate. So big picture, right? Keep in mind, we're making a ton of filtrate and the rest of the nephron is gonna sit there and pick and choose what should be reabsorbed, and then if anything additional should be secreted into it for excretion, right? So filtration. Now, this glomerular filtration rate, of course, is regulated by the body, and in the same way that we've seen in every other system. We start with autoregulation, we then move into hormonal and nervous system regulation. Nervous system is over here in purple. So let's look at this real quick, and then we'll wrap this one up. So basically what we're looking at here is how we control glomerular filtration rate. And again, we're going to start out with autoregulation. So the kidney itself can sense changes in that filtration rate and make adjustments, right? So what they're showing you here is this idea of disturbing homeostasis. So they're saying, well, if the glomerular filtration rate decreases, right? We're not making as much filtrate and therefore we're not making as much urine. The kidney makes some changes. Now here's a really cool one. We actually change the afferent and efferent. So in autoregulation, so let's see, how do I do this? So this is my afferent, this will be my efferent, right? If in response to low, that's the example they're giving us here, to a low glomerular filtration rate, the kidney decides to change the dilation of these two vessels to make it so that more gets pushed out of the glomerulus. Okay, so think about this. How would you adjust the diameters of the afferent and efferent arteriole to push more? Okay, so what we want to do is bring more blood flow. So we're actually going to open up the afferent. We're going to dilate the afferent arteriole, right? Like now, instead of like a garden hose, we want a fire hose, right? So we're going to make that bigger, more blood coming in, but then we're going to close off the exit. Instead of a garden hose, you get a straw, right? So we're going to constrict the efferent, right? And that is going to increase glomerular blood pressure and therefore increase our GFR, right? We get back to homeostasis. So just like that, right? Like real quick little change. They're also pointing out those mesangial cells between capillaries, they can constrict and adjust blood flow there. That is autoregulation, right? At the kidney, at the glomerulus, sorry, which is in the kidney, we make those small changes in afferent and efferent, and we fix it. Okay, that doesn't always work, right? If that's insufficient, we go up to the renin-angiotensin-aldosterone system, which you were hoping we would get to, right? We move on to some hormonal. Regulation. if you've got this, fast forward. If you need to hear it one more time, right? Remember that the liver is producing angiotensinogen, and this inactive protein is circulating in the blood. When the juxtaglomerular apparatus here at the nephron releases renin, we go ahead and change that into angiotensin 1, right? That's all happening up here in this first box. There's angiotensin 1. Angiotensin 1 is going to get converted to angiotensin 2. Where? By whom? In the lung by ACE, angiotensin converting enzyme. Sounding familiar? Okay, so we get angiotensin 2. Now, what I really like in this image is notice this, right? Angiotensin 2 causes constriction, right, of the efferent arterioles, upping blood pressure in the glomerulus. Angiotensin 2 triggers aldosterone. So maybe we can put all of these on here. Angiotensin 2 triggers aldosterone release, which we know is going to tell us to reabsorb sodium. Water is going to follow. We up blood pressure. Angiotensin 2 did vasoconstriction of that efferent arteriole, right? So the exit becomes smaller. That's going to up our blood pressure. And angiotensin 2 also triggers those neural responses, right? So we also get sympathetic nervous system involved here, right? And so in purple, they're showing you things like the nervous system response is to produce more ADH, right? So we reabsorb water, we stimulate thirst, increased sympathetic motor tone, right? So we're doing vasoconstriction kind of more systemically to up blood pressure. Let's do general vasoconstriction, right? Sympathetic tone to increase blood pressure, right? So all of these things, right, are leading to an increase in blood pressure, which is then going to increase glomerular pressure, right? Glomerular filtration rate. Okay, so autoregulation, hormonal, and then also the nervous system. Now, the thing that they don't show you on here is kind of the flip side, right? So remember, RAS is doing all this up the blood pressure, up the blood pressure, up the blood pressure, and just to make sure we don't lose track of it, sometimes it's too high, right? These are all showing you if GFR is too low. How do we fix it? How do we get it back up? But do keep in mind, if blood pressure is really high, we have those natriuretic peptides, atrial natriuretic peptide, brain natriuretic peptide, that will cause us to decrease blood volume and therefore blood pressure. So keep that one kind of tucked in the back of your mind as well.